So, Court, let's look at what we can figure out. Okay, it says this. Example 1, a mass little m, you know what, let's have little m be a rocket ship, like in the picture there, is moved from the surface of the planet to a distance big R from the planet's center. Move from here to here. Which of the following is true about the work done? And I've given you 1, 2, 3, 4, 5 possible equations. Yeah. Is it still oh, it froze. I've double froze it. Did I do that twice? There we go. Must have hit the button twice. Thank you. Is the touch screen on? Oh, I got to turn the touch screen off. Otherwise, that's going to drive me crazy. Sorry about that. Rather than look at all the answers, I think I'm going to try and derive the equation and just see if we can, as we go through, eliminate wrong answers and come to a consensus. Marcus, what does this question want me to find? So why can't I go, don't write this down, why can't I go force times distance? Because that's what work was last year. Why can't I just use that? Yeah, because it would really be the force of gravity, but as you move further from the Earth, gravity is no longer a constant force. I think that gets rid of A, because A is force times distance in disguise, is it not? Marcus, I could also find the area under a curve. Well, actually, no, because it's a curvy area, unless you have calculus skills, we can't find the area under a curve, and they didn't give me a graph anyhow, but that would be another legitimate option. So we have to go to our third definition of work, which was a bit more universal. We added this to our formula sheet. We called this the work energy theorem. We said that work was also the change in potential plus the change in kinetic. You okay with that, Marcus? Look at the picture. Looking at the picture, how fast does it look like the rocket is traveling on the Earth's surface? I think, if that's initial, I think my speed is 0, looking like it doesn't appear from the picture as though it's moving. You okay with that? And if this is final, does it look like the rocket is moving there at the top at all? Is there any exhaust coming from the nozzle? I think we can safely assume that. The other way you can safely assume that is if it was moving and it was a test question, I'd tell you. All right. Marcus, what's changing anything? So this is going to be PE final minus PE initial. Oh, potential energy, Mr. Dewick, that's easy. That's going to be MGH final minus MGH. Or is it? Why can't I just do that one? G is changing. G is changing. So I have to use my cosmic potential energy equation, which was negative big G, big M, little m over. Now R final, I think in my diagram, Priya, is capital R. Yeah. Minus negative big G, big M, little m, all over R initial, which I think in my diagram is just lowercase r. Taylor, what's a minus minus the same as? Okay. Can anybody spot which equation I think, Matt? D? Yeah. I don't think it's any of those. Once we have that minus minus, Taylor, which is a plus. Are you positive? It says explain your answer. You know, there's my proof. We derived it there. Okay. Now, that would not get you in orbit. That would get you high to a certain height, but as soon as you shut your engines off, you're coming crashing back down. You can't stay in orbit without some kinetic energy. To stay in orbit, you'd have to lift up, and then, Courtney, you'd have to turn the rocket sideways and fire the engine sideways until you hit just the right orbital speed to maintain your orbit. Or you'd do it at the same time. You'd go up in kind of an archy angle and get to the right height at the right speed. So I think I wrote here, oh yeah, no, not yet, sorry. Another concept, to escape from a planet's gravity. That means, in theory, to travel an infinite distance from the planet. Practically, in reality, what it really means is get far enough away from the planet so the pull of gravity becomes minuscule, negligible, meh. To barely escape means to escape from a planet and have no kinetic energy left. You time it so well, you run the numbers so nicely, Kareem, that you coast to a stop at exactly the moment as you are escaped from the gravitational field. Or in other words, you end up at rest and at an infinite distance. Dylan, what does this question want me to find? How much what? Well, I guess what's my final kinetic energy, Dylan? 0. And let's assume we're taking off from the North Pole. We're going to start at rest. I think we can say that. That leaves me with a change in potential energy. By the way, my writing is even messier than normal. I realize that. I need to calibrate my pen, but I'll do that tonight. Since they reformatted everything, that's another thing that's kind of wonky. It's set up for a right-handed writer, probably. I got to fix all that. Dylan, what's change in potential? What's change in anything? So this is going to end up being potential energy final minus potential energy initial. Now, final is out at infinity. How much potential energy do I have out at infinity? This is how we defined it. How much do we have out at infinity? 0. The phrase we used was relative to 0 at infinity. In other words, Dylan, I think I can actually say that as well because we've defined 0 to be infinity. So the work is the negative PE. Dylan, I think this is negative here, but there's also a negative inside there. You know what? I think I can get this. How much work would it take? Negative, and then negative big G, big M, little m, over our initial. Taylor, what's a minus minus the same as? I'm just going to scribble out both the negatives if you want to. Or I mean, you can put them both there too. But by the way, that is a positive answer, which Dylan does make sense because I would have to burn fuel to get out to infinity. So the math does work out. I was kind of hoping for a positive answer. It's not like you can fall up out to infinity. It's you have to burn fuel to get to infinity. Of course, you could also reach infinity, escape from the Earth's gravitational field, and still be moving. What would that equation look like? Well, it would still be work equals big G, big M, little m over R initial. That's how much energy you need to get out of Earth's gravitational field well. And then I guess you'd have some kinetic energy. That would, whatever speed you want, please tell me, Prith, that's how much extra kinetic energy I need. Okay. This is what we called, if you just reached a speed of 0, if you ended up, Matt, drifting to a stop right when you escaped the Earth's gravitational field, we called that speed escape velocity. Should be called escape speed, but it's called escape velocity, so I'll go with the vernacular. Like example 2, a 12,500 kilogram rocket blasts off from the Earth and barely escapes the Earth's gravity. How fast was the rocket moving at launch? Okay. John, is this question asking me how much work? No. In fact, what's this question asking me to find? Speed. Is there a change in height in this question? Psst. Is there a change in height in this question? Is there a change in height in this question? Yeah. Is there a change in speed in this question? Say yes. Is there a yucky curvy force, a changing force in this question? This is a job for conservation of energy, G, I think. But we're going to have to use the cosmic one. So we start out the same. We start out by saying, well, your initial kinetic and your initial potential equal the final kinetic and the final potential. where initial is right on the Earth's surface and final is out at infinity? Oh, what did we say our final potential energy was if we were out at infinity? So I can say, hey. And then I underlined barely escapes. What I mean by that, Courtney, is you had no extra energy left over. You came to a stop right when you also got to zero gravity. We get this. Kinetic energy hasn't changed since physics 11. It's still a half mv squared. I guess v initial squared. Plus, Krima can't use mgh because we're going cosmic. Negative big G, big M, little m, all over R, not final, Mr. Dewick, initial. That equals 0. Oh. John, if it's okay with you, I'm going to plus this over. Yeah. We'll get a half m v initial squared equals big G, big M, little m, all over R initial. What else do you notice, John? So the escape speed, escape velocity, it's the same for the space shuttle as it is for a tiny satellite. Doesn't matter. Now, you'll use more energy for the space shuttle. So if we were calculating how much work, then the little m is not going to cancel. But if we just need to know how fast, doesn't matter. How would I get the v by itself? And now, instead of calling it VI, do you mind, John? I'm going to call it escape. We actually did this before the break, but this is to both jog your memory and because it's kind of nerdily cool. In fact, I'm enough of a nerd. I know escape velocity from the Earth, it's 11,100 or 200. Or it's close to 11,000 meters per second. It's about 11 kilometers per second. So let's crunch the numbers and find out, just to see if we're right. 6.67 times 10 to the negative 11. Remember, big G is that universal gravitational constant. Don't let it scare you. It's just the number we have to put into our gravity equations so that we get an answer in newtons from kilograms, meters squared. Mass of the Earth is 5.98 times 10 to the 24th divided by, what's our initial? Where are we starting? Surface of the Earth, aren't we? So, John, what's our initial? I did not do this in my head. I'm going totally from memory, but I think you get 11,180 or something like that. Is that right? Yeah. I'll go 11,200. And that's meters per second. Courtney, how did I know not to handle this with work? Because it didn't say how much work. And I noticed that there was a change in height. At least I eventually noticed there was a change in height. Change in speed. Not a yucky curvy path, but a yucky curvy force. Hey, that's also a job for the law of conservation of energy. Okay. I like example 3. I like example 3. Example 3 is a nice question. You spilled? Oh. Priya, you may recall when we were doing the momentum collisions at angles, I told you that there was one question that was longer in terms of amount of writing than those cosine law monstrosities. This is it. Sorry, this is it if I just asked part 6, the last part. What is? Can you read me the last part, Priya? Find what? Keep going. That last phrase is key, to put it into orbit. In other words, you can't just find the work to lift it up like we did a couple of questions ago. You're also going to have to find the work to put it into orbit. It's going to have some kinetic energy as well. Here is that question, but walking you through everything that you need to find along the way. So if I asked you, hey, how much work to put a 12,500 kilogram satellite into a stable orbit. The 25,500 kilometers, is that a radius or an altitude? Read carefully. Is that a radius or an altitude? Sorry? Yeah, because it says from the. So it's a nice radius. So let's draw in on our picture. Let's go yoink. 25,005. Oh, wait a minute. It's 25,500 kilometers. We don't do physics with kilometers. Times by 1,000. And I think you'll get what in scientific notation? .55 times 10 to the, is it 7? So our orbital radius is that. If they had given that as an altitude, I would have just had to add the radius of the Earth into this on top of it. But they gave it to me from the center of the planet. Okay. You ready? What all can we find? Taylor, can you read part I to me? Did you say orbit? Gravity is what's pulling me in a circle. The word orbit, that tends to trigger that thought. Especially its orbital what? Speed or period or radius. I'm starting there. Gravity is big G, big M, little m, all over r squared. Which r? Well, we're in orbit, so if you want to, you could put an r orb squared. And that's going to equal, now Taylor, force is always mass times acceleration. Don't write that down. Mass times acceleration. Circular force is mass times circular acceleration. Don't write that down. I have two equations for circular acceleration. Which one am I going to use? Well, what are they asking for, Taylor? So I'm going to use the one that has the speed in it. Which is which one? It's on your sheet. This is to jog your memory. I know, it's been a while. Thank you, Lydia. Thank you, Taylor. Yeah. What if it had said period? 4 pi squared r over t squared. Okay. I should be consistent in my colors. V squared over r. Now, you might recall, sometimes the r canceled, sometimes the r didn't cancel, and you ended up with an r cubed. Here, does the r cancel? Well, you can imagine the r on the right can move up to the top. On the left-hand side, you'll have one r up top, an r squared on the bottom. Here, one of these cancels. In fact, Taylor, what did you say we're trying to find? How would I get the... Oh! That cancels as well, quite wonderfully, yes? How would I get the v by itself? How to get rid of a squared? Yep. So... we derived this equation a while ago. You can memorize it if you want. I deliberately did not put it on your formula sheet because, again, Dylan, you know I tend to derive rather than memorize. But we did get that orbital speed was equal to big G, big M over R. Under hashtag cool nerd trivia, that's orbital speed, where we're talking about R as the orbital radius. Escape velocity was put a 2 in front of the G and start out on the planet, so R would be our initial. But I do like there's some lovely kind of symmetry. Wow, this stuff is all related going on here. All right, time to plug and chug. 6.67 times 10 to the negative 11, 5.98. No 2, Mr. Dewick. I got orbital speed in my I got escape velocity in my brain. Times 10 to the 24th divided by 2.55 times 10 to the 7th. Pretty sure the answer is going to be less than 11,180 because that would get us out of the planet. What do you get? 3950, is that what somebody said? It sounds familiar. 6.67. Again, if you're not practicing with your calculator, you're setting yourself up for some ugliness here, because these are not that easy to type in. So you'd rather make your silly mistakes in class. I'm going to write 3955. I'll carry the extra sig figs because we're going to use this. And I guess that would be meters per second. Good John, Kevin? Ready? Kevin, what does part 2 want me to find? Kate. I'm a little worried because there's a TOC next door. I'll ignore that, though. We'll just hope. KE, kinetic energy. Okay. Kinetic energy hasn't changed since Physics 11. That's going to be a half mv squared. And I guess, Kevin, v orb squared, right? That would be the kinetic energy in orbit would be a half mv orbit squared. 0.5. Kevin, what's little m? Did they tell me the mass of the rocket? What's little m? Did they tell me the mass of the rocket? It's in there somewhere. What's the mass of the rocket? Psst. 12,500? Yep. Yep. And then, what's my orbital speed, Kevin? Psst. What's my orbital speed? 3955. And if you have it still stored on your calculator, you can just use your answer button. I'll write 3955 squared, but of course I'll use my answer button. Before you guys, some of you already hit equals. I already know because I've done a bunch of these, and I think I mentioned to you, typically your energy is going to be in the 10 to the 10th or the 10 to the 11th range. If you don't get something with a 10 to the 10th or the 10 to the 11th, just double check. It may be I gave you a weird example, but double check. You 10 to the 10th, I believe, yeah? No? Yeah? A half m answer button squared. Yeah. 9.776 times 10 to the 10th. Units, it's energy. Joules. .776 times 10 to the 10th. Ethan, what's the third thing they wanted me to find? I've scrolled down now, you'll have to tell me.
It's potential energy running orbit.
Oh, potential energy in orbit? Why can't I just go mgh? Okay, gravity's changing. So, Ethan, we're going to have to use our cosmic potential energy, which is negative big G, big M, little m, all over our orb, right? Yeah. Which is going to be lots of typing. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 12,500, I think, was little m. Yes, I hope. Divided by 2.55 times 10 to the 7th. What do you get for the orbital potential energy? Do you get 1.95522 times 10 to the 11th? Or not? Negative, but that magnitude? Okay. Don't ask how I cheated, Taylor, and I'll show you the shortcut in a second, but you should get that, but okay, times negative 1. Fair enough. You get negative that. And it's exactly that, isn't it? Those digits?
Yep.
Mr. Duick, you didn't type all that. You just went this number times 2. Yeah, I did. Patience. There are clever shortcuts that you can survive without, but one of the things I'm going to do today, Marcus, is show you some of the clever shortcuts as well. I am going to write down the answer. Negative 1.955 times 10 to the 11th. Mr. Duick, how can you have a negative energy but be up high? Where did we define zero at? Out at infinity. So to get to infinity, would you have to burn fuel? Would you have to add energy? Then you better be starting out negative if you're going to add energy and end up at zero. So this doesn't, it's a little weird at first, but this is, since we've defined zero out of infinity, this is okay. Okay? Kareem, what's part 4 want me to find?
It's total energy in orbit.
Total. Huh. Total. What would the word total suggest? When I say total things up, what mathematical operation are we usually talking about? You know what? I think total energy is just going to be the potential energy in orbit and the kinetic energy in orbit. In other words, I think it's going to be your answer from part 3 plus your answer from part 2. Yes? It's going to be negative 1.955 times 10 to the 11th plus positive 9.776 times 10 to the 10th. And I'll bet you when you do that, you get negative 9.776 times 10 to the 10th joules. I'll bet you. I'll bet you get this number there. The reason is, by the way, Prith, we're going to find in a second that kinetic energy in orbit, potential energy in orbit, and total energy in orbit, they are all very related. If you know one, you can find the other two pretty cleverly. Did you get 9.776? Or are we off by 1 decimal because we rounded? No, we're good? Okay. Negative 9.776, right? Sorry. Again, why negative? Because you'd still have to add energy to get out to infinity. You okay with that, Matt? What's the last thing they want me to find? No, not the last thing. There's 2 more. Matt, what does part 5, part V, want me to find? Potential energy at launch? Do you mind? Can I call that PE initial? Because I think that would be launch. Well, that's going to be negative big G, big M, little m over R initial, which is going to be negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 12,500. Matt, what's R initial? Well, we're starting on the surface of the Earth, so I guess that's R initial. So what is that? That's why I'm asking you. Have I got enough room? Oh, good. So it's going to be negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 12,500 divided by 6.38 times 10 to the 6th. Double check for typos. I think that looks good. Do you get negative 7.81477 blah, 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 blah times 10 to the 11th? Okay. Negative, what was it, 7.815 times 10 to the 11th joules. Whew. Whew. Rylan, what's the very last thing they want me to find? Work. So I would have no problem skipping all these intermediate steps and just asking you this last bit, because watch. Work is going to be the change in potential plus the change in kinetic. Rylan, what's changing? Anything? It's going to be PE final minus PE initial plus KE final minus KE initial. Now, when we're launching into outer space, we said we're going to assume we're launching from the North Pole unless the question says different. Assume you have no initial kinetic. What's your final kinetic? Well, isn't that really the kinetic energy in orbit, the 9.76 times 10 to the 10th? What's your final potential? Isn't that potential energy in orbit, the negative 1.995 times 10 to the 11th? What's your initial? Isn't that my answer from part 5? Okay. So, here we go. Final, what was it? Negative 1.955 times negative 1.955 times 10 to the 11th minus negative 7.815 times 10 to the 11th. There's my final minus initial for potential energies. Taylor, you'll notice what's a minus minus the same as? Are you positive? And then plus 9.776. This should end up being a positive answer because it should take work, it should take rocket fuel to put something in orbit. Negative 1.955 times 10 to the 11th minus answer, there's my minus minus, which is plus 9.776 times 10 to the 10th. Whoop, almost made a typo. Good thing I caught that. 0.955 instead of 9 point. Negative 1.955 times 10 to the 11th minus negative, the minus minus will give me a plus 9.776 times 10 to the 10th. Do you get 6.84 times 10 to the 11th? Yeah. This would be a fair game question to ask on a test, but I'll be honest, I wouldn't walk you through part A, part B, part C, part D, the first 5 parts. I would just say, hey, find out how much work, and then you'll have to calculate what you need. Now, typically, Lydia, what I would do, remember the ditto marks thing that I showed you in the back? That's how I would do it. I would find the change potential separately on one line, write it down to like 5 sig figs, find the change in kinetic. Oh, they didn't give me the orbital speed. Gravity is what's pulling me in a circle, and then add them up. Whew. Remember that shortcut that I used where I just times by 2? So example 4 says this. Now example 4, this one here, Kareem, I'm totally showing you for nerd value. You can survive perfectly fine without it. I've never really bothered memorizing it. It's just kind of cool. It says, using the expression for orbital speed, which is square root of big G, big M over R, Taylor derived that one, prove that in a circular orbit, kinetic energy is half the magnitude of the potential energy. Say, what? Hey, Taylor, let's you and I do this together. What was the equation for kinetic energy? It's been that since physics 11. KE equals a half. Yep. Only this time I'm going to put orb squared. That speed. This speed. Which I guess means I can go a half m, and then it'll be the square root of big G, big M over R squared. Folks, what happens when you square a square root? They wipe each other out. So we're going to end up with a 1/2, an M, a big G, a big M, and an R. I'm going to write it slightly different order. I'm going to write the 1/2, but if you don't mind, I'm going to put the big G first, the big M next, the little m, and then the R. If I just gave you, don't write this down, look up. If I just gave you that with a negative, what equation would that be? Show that kinetic energy is 1/2 the magnitude of the potential energy. Yeah, it is. It's positive where the other one is negative. That's why I said magnitude. But there, we just proved it. That's why when I had the kinetic energy, I cleverly just doubled it because I knew that was the potential energy. It's a nice shortcut. But you can survive without it just fine. Kareem, what does part 2 want me to show? Total. What does total suggest? Mathematically, what should we do for totaling something? So I think I'm going to go PE plus KE, and these are both in orbit. Kinetic energy, potential energy in orbit is negative big G, big M, little m over R orb, plus kinetic energy. Taylor, I'm going to drop your expression down, what we just derived. 1/2 big G, big M, little m over R orb. Cream, is there a big G in everything? Yep. Sorry, let me be careful. Is there a big G in both these terms?
Yep.
Big M in both these terms?
Yep.
Big little m in both these terms? An R orb in both these terms? Yep. I'm going to argue, Kareem, this is exactly the same as negative x plus 0.5 or 1/2 x. I'm going to argue those are like terms. They are. What's negative 1x plus 1/2 x? So negative 1/2 expression. Negative 1/2 big G, big M, little m over R orb. Kareem, can you read to me the statement for number 2, what we were trying to prove?
Total orbit energy.
Stop. There's the total orbit energy. Is what?
Is
half the potential. Yeah, it is. Huh. Okay, so I used that as a shortcut as well. I think I divided by 2 to find something for total. Yeah. They had some flooding in one of the Miss Kim's room flooded over spring break, so they're trying to dry it out, and they're all through there. Lydia, what does part 3 want me to prove? Stop. That's this one right here. Sorry, let's get that. That's this one right here. Keep reading. Aren't they identical, but one's got a negative, one's not? Isn't that the definition of opposite? We proved it, I think. Okay. Again, John, don't sweat over those relationships. You do not need to have them memorized. That's me, nerd trivia, nerdily cool. It's kind of neat that they are so wonderfully linked, but I've showed you how to derive them all from scratch anyways. I want to look at the various situations I can throw at you, and specifically I want to ask, Mr. Dewick, when do I use work and when do I use the law of conservation of energy, G. All right. So we're going to look at several situations here. Situation A, a rocket is at rest. I probably underlined the word at rest. On the surface of the Earth, it blasts off from rest. Since I said it twice, that's probably important. Rises to a maximum altitude or height h, to a maximum distance big R. Write equations to calculate the work done. The what? The work done by the engine. And again, we can assume the rocket begins and ends at rest. I let you off too easy, Lydia, so we're going to do this one together. What does this want me to find? Calculate the? Work. Work is going to be change in potential plus change in kinetic. Can you read to me the very last sentence, Lydia? I think we can safely go. This is asking how much fuel, how much work, just to lift it high enough to get to the orbital radius that you want. You're not keeping it in orbit yet. It's going to come crashing back down, but let's pretend little visible angels or something are holding on to it. Okay? What's change in anything? And you would use cosmic potential energy. I'm not going to go any further because I didn't give you numbers. I'm going to say you can take it from there. I just want to start the approach. So yeah, this is how much work to lift something. This will not keep it in orbit. Why not? No KE. What other kind of questions can I ask? A rocket moving at speed v at liftoff. So now, instead of starting on the ground at rest, let's pretend we're like a centimeter above the ground. We've already hit full speed. Rises to a height h with no engine use. We fire our engines on the ground, and then we shut them off, and we coast the rest of the way. Write an equation to calculate the maximum height using conservation of energy. Using what? So it would be KE initial plus PE initial equals KE final plus PE final. Priya, what does this question say we can assume? So I think I can do that. Let's go a little further with this one. KE, what's kinetic energy been since physics 11? A half mv initial squared. And I guess initial, this would be the speed that we left the Earth's surface at. Plus negative big G, big M, little m, all over R, and I'll write the word Earth, our initial planet, surface, right there. That equals negative big G, big M, little m, all over our final. And what this question wants us to find is our final. I would not try and get R by itself. Dylan, what I would do is I would do the entire left-hand side and turn it into one number. So I have one number equals negative big G, big M, little m over R. And then I would cross multiply to get the R by itself. But I would do that after. I would not try and do it right now. Problem, this is not what the question wanted me to find. What did this question want me to find? Calculate what? Maximum height. This gives me the radius. This gives me that's our final. How can I figure out the height? Okay, so if they actually want the height, that's going to be our final minus our Earth, whatever the heck that is. Will I ask you for the height? Yeah, maybe once, I don't know. I mean, if you can do it once, you can do it every time, but that's overkill in my mind. All right, what else could I throw at you? Here's a rocket moving at speed v at liftoff, so initial kinetic energy is not 0 this time. And it barely escapes with no engine use. They fire the rockets, we turn the rocket off, we coast. Write a conservation of energy equation that will allow us to solve for V. Oh, where do we end up? Where do we end up? Oh, out at infinity. You know what? This is escape velocity, which we already derived. I think it was 2 times G times R, times M over your initial. I think it was that. If you want to do the actual derivation, we did it earlier. I think it was example 2 or 3, something like that. Okay? So I would start out, I see some of you looking a little stunned. I would start out with conservation of energy, G. It's just that your final kinetic and your final potential are all 0. So you get the left-hand side equals 0 plus the negative potential energy over, and then get the V by itself. What else can I ask? E. Hedrick, what does E want me to do?
Work.
Oh, how much work? Wait a minute, Hedrick. Didn't I do that for part A? How is part A and part, what are we on, E? How are these two questions very different? And they are. Oh, so that means the one you and I are doing is tougher. The fact that we're in orbit means there's going to be kinetic energy. Now, it does say that we started at rest. So the work is going to be change in, well, you know what? PE final minus PE initial, there's my change in potential, plus KE final minus KE initial. Hedrick, I could do that. It does say, assume we're launching from the North Pole. PEs will be cosmic. I could go from there. What if they didn't give me, because kinetic energy is a half mv squared, what if they didn't give me the speed? Gravity is what's pulling me in a circle. We would use Taylor's equation. Right here I can find the orbital speed, which means I can find the kinetic energy. That's about the longest question I can throw at you in terms of, no pun intended, work. How much writing you do. All right. F. Satellite moving at speed v at a distance r from the Earth's center falls to the Earth's surface. Prith, what does F want me to find?
Speed.
Speed. Speed. Did it ask for work?
Nope.
So I'm not going change. Okay. Is there a is it an orbital speed that it's asking me to find? No, we're crashing. Okay. So I'm not going to go gravity that's pulling me in a circle. Is there a change in height in this question?
Yes.
Is there a change in speed in this question? Is there a yucky, curvy changing force? This is a job for conservation of energy. G. It's going to look like this. KE initial plus PE initial equals KE final plus PE final. A half mv initial squared plus negative big G big M little m all over R initial. Now in this case, R initial would be the larger one. We're out in space. And when we get to the Earth, R is going to be typically Earth has been our initial. This time Earth is going to be our final. That's going to equal a half mv final squared plus negative big G big M little m all over R final. I do notice it doesn't matter the mass of the satellite. They're all going to hit the ground the same speed. Now, the damage will depend on the mass of the satellite, very much so. But the speed that it hits won't. What am I trying to find here, Prith?
Speed.
Which one?
Here.
Which one?
Fine.
That one there. I would not try and get the V by itself. I would instead, plus the negative big G, big M, R final to this side, get the whole left side as a number, and then I'd times by 2 square root at the end to get the V by itself. But I wouldn't do it all at once. As much as I love to do that, I would say no. What's your homework? Number 1 is good. 3 is good. 4 is good. Please notice with number 3, what planet or what celestial body are we dealing with? The moon. Make sure you use the mass of the moon. Don't use 5.98. Make sure you use radius of the moon. Don't use 6.3. I like number 5. I like number 5. I like number 5. Number 5 is a nice question. Seven and 8. Please notice they're in kilometers. Well, the 8 is. 13 is good. 15 is good. Class ends at 1:30 or 1:35? 1:30? I'm 60 seconds short. I can't show you the video that I wanted to show you. I'll have to show it next class. Rats. My timing was a bit off.